Okay, good morning or good afternoon or good evening. This is the second part of the video or that class session that I had on Thursday. As I promised that I'm planning to go through cover the material in chapter 4, the rest of the material that couldn't cover that day. Okay. So we can remember that up to that point, then on the Thursday during the class session, that during that particular period of time, or that when we were recording that video, that video is already available on Blackboard, and we were talking about that not a one variable, two variables, how one variable going to affect the other one. Under this discussion, we had like a broader discussion on this one, very broad discussion. And then we did that one in actually the way that I presented you that in two ways. Two ways means like a barely I mentioned that what kind of a statistical or data analytical procedures can be utilized in order to explain one type of variable by the other type of variable, like that. Those are statistical procedures. The other one, when you have a one type of variable, how that can be explained by graphically. Mainly we focus on the graphical representation and the numerical presentation under this two variable discussion. That means you can remember I just drew some kind of like a box. In that box that I mentioned that there are two types, mainly two types. That means that which variable gonna go to x-axis, and the other variable, the variable that's going to go to the y-axis. So based on that, where they're going to appear, we call them with the different names. Then if that particular variable is gonna go to x-axis, we call that one explanatory variable. If it's gonna go to y-axis, we call them the outcome variable. Outcome has been explained by the explanatory variable. But again, we went a little bit further down and say even within the explanatory variable, it might gonna be that particular variable can be either that categorical or quantitative. That so does with the outcome variable. In that way, we have four options. Under these four options, we discuss what are the graphical representation. That means if I'm gonna get back to or recap or try to refresh your memory, this is exactly what we did last time. Okay, I'm gonna summarize what we did last time. Okay, mainly graphically. Okay, before that I'm gonna share this screen. I'm gonna share the other screen. Okay, so you can remember, I'm gonna open this one. I'm gonna talk about that one here. Okay, I'm gonna start from a new page and then it will go through that one. I talk about, see, mainly we have two types of variables. One's going to go to x-axis, which is called the explanatory variable. Explanatory variable, I'm going to call that one var variable. Under that one, it may be either quantitative or categorical. See, pretty much just in a similar fashion, we had the variable which is going to go to y-axis, which is called outcome variable, outcome var. Again, that variable may be either, see, categorical, quantitative or categorical. Okay, we discuss about that one based on different examples. Okay, then we told that when it comes to quantitative, y variable would be the thumb length, categorical variable would be, see, we were talking about something here, see, in the very beginning. That means thumb length being explained by the gender. See, thumb length being explained by the gender. You can remember that we talk about example. Anyhow, that before we have talked about that one but statistical procedures. I'm not talking about the statistical procedures. What would gonna go with this setting? Okay, this setting. Or if you have a quantitative, we mainly do something called regression. See, regression. If you have a quantitative y variable and categorical variable, we're going to do some group regression. Group regression. Or something called analysis of variance. We don't do that one in this class, but that's the procedure we're going to do. Okay, statistical. If you have a quantitative X and categorical one, we're going to do something called the logistic regression. Regression. If you have a quantitative, qualitative, categorical, we're going to do something called chi-square test. Those are statistical procedures. For the same thing, we were looking for the graphical representation. How do you do this? And this is statistical procedure. What are the graphical procedures? See? Graphical procedures. Then we had X would be explanatory variable. And the Y would be outcome. Okay. I'm going to make it a larger one. See, under this one, we had quantitative, and then we have a categorical. Again, we have a cont, in cont on this box. Here we have a categorical. See. Under that, when the Y outcome is quantitative and when explanatory variable is categorical, we drew something called what? Not the histogram. We did the what? Stack histogram. First one, stack histogram. Can you remember? We did the stack histogram. Number 2, we did the vertical faceted histogram. Faceted histogram. Then the third one, we did horizontal faceted histogram. Then the fourth one, we did the what? Dot plot. With the dot plot. Then we did the jitter plot. See? Dot plots, okay, jitter plots. Then we did what? Box plot. Box plots. Then we did the jitter plots. Jitter and box plot together, box plots. See? That you can remember what we did. See? These are the 7 types of plots that we did if the explanatory variable is categorical and the Y variable, outcome variable, is quantitative. And on the other hand, when the categorical variable, and for the categorical variable, we did that one, again what? Bar graph. Can you remember? Categorical, we did what? Faceted, vertical, faceted, bar graph. Second one we did horizontal, faceted, bar graph. See, we did all this. Okay, we'll talk about that one in large scale. They are codes. We're not going to do anything by hand. We did everything by see, everything by what? Everything by using the R. Okay. Then later on, when you have a quantitative and quantitative, you can see that one. Quantitative and quantitative. Quantitative Y variable, quantitative outcome, and the quantitative explanatory variable. We're going to do something called the scatter plot. Scatter plot. We come to that one too. Okay, that's only one scatter plot. How about the quantitative but categorical? We don't discuss that one. Okay, no discussion. So you're going to talk about the scatter plot. You're going to talk about this guy. You're going to talk about these guys. See, large scale. See, for when you have those, when it comes to that, write in the codes. Write in the codes. Okay, I'm going to get this one to a little bit here. You can remember what are the codes that we're going to utilize. If you want, I can go back and then write that one within this box. In that way, it's going to be very easy. So that means, okay, if I go to, okay, give me 1 second. I'm going to go to chapter 4. We are on chapter 4. Chapter 4, string variation. Okay, then, okay, give that one. Okay, if you do that one stack, I'm gonna write the codes related to this each and every variable. Okay, this one again. Okay. I'm gonna get more space over here. I'm gonna raise this one a little bit. Okay. Get this one. I'm gonna get this one. Okay. Then I'm gonna get this one. And here I'm gonna say X explanatory variable. And here you have quantitative, here categorical. Okay. I'm gonna leave more space for them to write here. The whole thing, this is Y equals outcome variable. This one is cont. No. Okay, I need another line. Okay, this one stays as it is. I need another line. This one like this. Connect with this one. This is Y. Okay. Y equals variable. This is QUANT count. This CAT category. Okay. And okay, first one you can remember stack one. Can you remember stack histogram? GF underscore histogram. Okay, histogram based on that quantitative variable sum. See, that's the quantitative variable which is Y. See, then data. You can remember that fingers. Okay, data fingers. Okay, come on. For the fill, you put, see, again on X, the gender. Or you can do the same thing, GF histogram for thumb, which is quantitative. Okay, quantitative, go to data, which is fingers. Instead of that one, you can do with the color, but it's gonna come to X-axis as well. That's why we're gonna write tilde. See, tilde. See, then you have the stack 1. Okay, this is completely corresponding to what we had on the other page. Okay, I'm talking about that if you want to get the stack histogram, how to get that one. You have a quantitative, see, y, which is, see, but it's going to put on x-axis. Okay, y variable and x variable both going to be put on the x-axis. Once you draw that one, you saw that how it looks like. See, see how you draw. See, it looks like this. Then you can do the other, make it like a fancy one later on, but this is the way how you can do. Okay, see, sometimes I'm gonna, on this page, what I'm gonna do, I'm gonna allocate this one only for, sorry, only for quantitative, because I don't have enough space, look like. Okay, so count only, y variable count only. I can write the rest on the other one. Okay, so then the second one, you can remember, I'm talking about how to get the, instead of that stack 1, you can get the vertical faceted grid, faceted histogram, vertical faceted histogram, vertical one. Okay, vertical faceted histogram. If you want, you did this one, GF underscore histogram. Okay, again you're gonna have that thumb, which is quantitative variable on x-axis. That's why I wrote that one right after the tilde, data, fingers. Now this gonna be connected or chain with the facet function, GF facet grid. That's the function. Grid how? That means you have to do this one vertically. If you want to do vertically, you have to see this is the vertical axis. That means everything has to be, see, the variable should come on y-axis. See, as I wrote before tilde, see, and then put the dot to say it's gonna drop down through that vertical axis. See, this is what I'm talking about. Okay, like that. See, and female being spread out. Okay, you saw that one, but I'm just refreshing your memory. Okay, then the third one, horizontal one, is similar to this one, GF histogram tilde, that's going to go to x-axis, thumb, comma, data equals fingers, okay, comma, sorry, close it, and it's been again chain with, see, chain with this one, GF facet underscore grid. This time it's going to go to X. That means after the tilde, but you're going to switch because they're going to appear horizontally. Okay, so that means you're going to put this one like that. See, that means the gender. See. Look at this one. I'm talking about this one. See, it's going to fill in that. See, it's going to fill that vertically, not vertically. I mean, like this is fixed. See, it's going to go this way. See, that's why it's fixed. See, that's why this is fixed. Okay, that's right. Then the fourth one, you can remember we mentioned for the fourth one, dot plots. Okay, let's go ahead and look at the dot plots. How to get the dot plot, what the command would be. Okay, give me 1 second. Okay, excuse me. Okay, I'm on the number 4. Dot plot you can get, again, you're gonna go GF point. This time you're gonna put everything in the same frame, rather than go to the two frames. So rather than go to two boxes, you're gonna keep everything frame. So you're gonna keep the Y. This time you're gonna have that thumb length in Y, tilde, then gender. See, and you call the data. See, data is fingers. See? That's how you're gonna do that. That's how you get this one point. See, I like to call that a point plot. Okay, do adjustment and everything and then make it fancy, that's a different story. But next one would be something called the jitter plot. Rather than having like that way, you're gonna spread out. Okay, so the fifth one, jitter plots. So you're gonna say GF JITT jitter plots, thumb, again go to Y, tilde, gender, sex, data, you call data fingers. That's how you're gonna get this guy. See, this guy. Do the color change and everything. That's a different thing. See, scattered over male and female. See, so the thumb length is gonna go to Y. Okay. That one. Okay. Number 5. Okay. See number 6. Number 6, box plot. You can remember how we did the box plot. Okay. Okay. I'm gonna do that one on another different page. See, number 6. Okay. So the box plot. See, that one is done by GF underscore box plot. You're gonna do the same thing like the thumb, like a jitter and the point plots. Same thing. Only thing you're gonna change the function. Fingers. See, that would give you box plot. See, box plot for male and female. See, I'm gonna talk about this one in detail later on. Okay, but before that, I'm just recapping or that refreshing your memory for what we did. And the 7th one, the last one, was you did jitter plots and box plot together. Okay, jitter and box plot together. Okay, so how do you do that one? GF box plot. Okay, you're gonna do the way that we used to do that one. Thumb box plot first, or thumb, sex, data, fingers, and this should be now chain and then connected to jitter plots. You simply say, hey, give me jitter as well. See? You don't have to put anything inside. Everything's already done. That means then you're going to have this guy. See, box and jitter together. See? That's when we have a quantitative and quantitative. That's why I'm going to stop over here. This part for the, see, categorical. See, on the y-axis, it's the categorical. See, CAT, cat variable. See, that's for y. Okay, y. See, then if you go to this side and then looking, not this one here, see, you have a vertical faceted bar graph and horizontal faceted bar graph for the categorical and categorical scenario. Okay, let's looking into that one too. Okay, what are the codes that's going to be utilized to get these two done? See? See? See, what is the code that you're going to utilize in order to get that one? Vertical and horizontal. See, we have to look into that one. Okay, so we can remember that we did that one yesterday. See, facet grid. To create a bar graph first. Okay, I'm talking about some kind of situation. See, so the first one is vertical faceted bar graph, vertical faceted bar graph. You do the bar graph first. GF, okay, bar, bar, and then should be drawn for what? It should be drawn for not the thumb length. This time we're gonna say weight lost. See, weight lost, and the data gonna be. We say that we were using different example. Mindset data set would be mind set matters. Mindset, I think this is small. Mindset matters, and this should be chain with facet grid, GF facet grid. Since it's vertical, we're gonna do by, you go to what? By condition. Condition would be the this one condition, this one dot. See, condition, then tilde, condition, then tilde, okay, then tilde. Okay, I'm gonna write here correctly. Condition, then tilde, see, and the dot. Okay, with a y, it's gonna go to y. It's gonna go to y. See, condition gonna go to y. See, can you remember that when we had that this one I'm talking about it. Here, vertical faceted grid. See, vertical one. See, vertical faceted grid. Vertically they were put down. Then you see, this is how we did that one. See, it's gonna see vertically. It's gonna go down. See, this is the y. It's gonna go to y. See, see. The vertically means see, vertically, horizontally like this. Okay, so the same way vertically it's go down. Okay, then its counterpart, second one, is pretty much the same way. GF bar weight lost. Okay, it's gonna go to x-axis, comma data, because mine set matters. Okay, then chain with facet, GF facet grid horizontally. Horizontally means gonna go to horizontally. You're gonna have that x-axis. Okay, so if you're gonna go to x-axis, you're gonna write this one. After this one, you're gonna write condition. Before that, you have a dot. See, dot, then tilde, then condition. See? These are the codes in order to draw this. Okay, and draw this graph, and then I'm gonna add something over here to see. This is a quantitative. This side quantitative too. See, x variable. See, count. Here I'm here. That one I'm gonna can give you ahead of the time too, how to get the scatter plot. Okay, that's a scatter plot. Can you remember? There you have a scatter plot. How to get the scatter plot? Let's see how to get the scatter plot too. I'm gonna give you heads up. Okay, I'm gonna give something ahead of the time. See, now the jitter plots. Jitter plots come for quantitative, categorical, quantitative. Okay, I'm gonna give that one ahead of the time for you to have like all the information at one place. Okay. One place. See. Yeah. For that one, we're going to use the same thing that we used over here, only different GF point. See, point. You put the y variable. Y variable, let's say that you're going to talk about the thumb length versus height. Okay, thumb, tilde, height, comma, data coming from fingers. See? You can do like that. Again, you use the GF point. Okay. So these are the graph you're going to see. See, this is for the count and count. This is for the categorical and count. It's going to continue all the way to the next page as well. This is for the categorical to categorical. See, now you have a clear picture what's going on. Okay, right. Now it's done. Okay, so that's the kind of like a refresh in your memory. Okay, so what I want to do, where I stopped last time, something. Okay, something. Okay, something here. I stopped 4.4 here. See, we did this one, we did this one. This is the place that we stopped. We had a serious issue how this can be done. So this is related to, okay, box plot. You know that I mentioned about this is called the faceted box plot. No? Sorry, faceted, we call, what do you call that? No? Let me see, box plot, no, not the histogram, see, not the faceted, box plots, okay, whether for the both cases, box plots. But when it comes to that box plot, we have an issue that what do you call this place and this place and this, we talk about that, forget about the both box plots for the male and female, but for one, so just a single variable like that, which we discuss in chapter 3. Okay, therefore, before I'm going to go through the 4.4, I would like to get into this one. Sorry. So this one, 3, okay? 3 point examining the distribution, which is 3.7, where that we're going to talk about the box plot. Can you remember? For the first time we talk about, we can draw the, okay, box plot by having that variable on y-axis. See, now remember how we did that one? What was our code? See, this is how I did this one. See, because here we put the number, but when we're going to draw this one with another variable, we put that other variable name here. That's a different story. But anyhow, it's a single variable. If you do this one, you saw something like this. Okay, you want to see something like this. See, it's the plot. Okay, it's the plot. We don't have any issues with this one. And okay, let's say that I'm gonna bring this one over here. Okay. So then we have, now we talk about the box plots. Okay, I'm gonna do the vertical box plot. You have a box here to represent something. Then you have something called the whisker. We told that this is gonna represent Q3. This somewhere in the middle line represent Q2. This one Q1. Here maximum. That's the end of the whisker. This is the end of the whisker. On the bottom side, on the below that one minimum. See, those are 5-number summary. That's the graphical representation of 5-number summary. Graphical representation of 5-number summary. That is min, Q1, Q2, Q3, and max. Okay, those are the 5 numbers. So we're not going to talk about the outliers. We just simply say that those are the places. See, those are the places that we can see that one. Let's say that for instance, if somebody want to calculate how you get the Q1, Q2, Q3 quartiles, how do you calculate quartiles? See, so then let's say that for instance, let's say that, okay, I'm trying to say an example. I'm going to talking about that we have a data set. Okay, I'm gonna just show you something. Data set. It's starting from 199 to 1, 236, 269, 271, 278, 283, 291, 301, 303, and 341. See, this is the data set. This is the data set. Okay, that's the data. 1, 2, 3, 4, 5, 2, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See, so therefore, sample size, which is denoted by n, is 11. See, we have 11. If you have that kind of we have a small data set like that, how could you gonna calculate the quartiles? Okay, how do you get the quartile? See, it's easy. So what are you gonna do? If you need the quartile Q1, see, lower quartile. I'm gonna say lower quartile. Lower quartile is nothing but the Q1. See, quartile 1, Q1 is given by 1/4 that 11 plus 1 term. See, 11 is your n. This is your n. See, n plus 1 term. Excuse me. So this is gonna be 1/4 12, which is the third term. If you get back to this ordered data set, see, it's had to already been ordered. If not, you have to order from the smallest to the largest one. Okay. Third data point means like a C, which is 236. See, 236. See, 236 is the third. See, therefore Q1 is nothing but 236. See? 6. Then you can get the middle quartile. Middle quartile, which is called Q2. Sometimes call this one the median. Middle one called the median. How do you get that one? 1/2. You put the 1/2. 11 plus 1. See, this is n. Okay. So that means 1/2 12 term. Okay, that's term. And that means 6th term. Go to the 6th one. So if you get back to this one again, we're going to count 1, 2, 3, 4, 5, 6. 278. 278 would be Q2. It's a 6th term. And if you want that upper quartile, which is Q3, it's nothing but 3/4. Actually, the second one is, you can say the 2/4. Okay, if you want, you can say 2/4. It's the same thing, 2/4. Okay, 2/4 is the 1/2 later on. 3/4 of 11 plus 1 term. That's the n again. See? That means 3/4 times 12, which is 9th term in that data set. We're going to come to here. We're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. 301. See, 301. 301 would be your I'm gonna draw that 301. See, Q3. Q3 would be 301. See? So that means this is Q1. See, Q1. 230 is Q2. This one is Q3. See? So once you get that one, how do you draw the system? This one. Okay, let's draw our box plot. Okay, the box plot. I'm gonna draw the box plot. I'm gonna say that my minimum value is nothing but how much? 199. And the maximum value is nothing but, max value is nothing but 341. My Q1 is nothing but 236. I'm gonna the Q3 first. Q3 is nothing but 301. And Q2 is nothing but 278. 278 somewhere here. See? 78. See? Looks like that. But okay. So what's gonna happen? Even though it looks like this one, sometimes some data points. See, and on the other hand, the height of this box. See, height of this box. See, height of box is nothing but interquartile range. Interquartile range, which is abbreviated as IQR. How do you get IQR? Is nothing but Q3 minus Q1. In this case, Q3 is 301 minus 236, which is 20. Is that Q3 minus Q1? 36. Q2. Q1. Q3 minus 11. Okay. 11, this should be 5. It should be 10. Should be 75. 9 minus 3, 65. 65. See, 301. 301 minus 236. Q3 minus Q1. See, 11 minus 6. 301 minus 236. 301 minus 236, which is 65. Okay, 65. 65. See? That gap is 65. Height. See? But when we're going to put the data into this one, some data we suspect going to be outliers, unusual. How do you figure them out? If any data fall above Q3 plus 1.5 times IQR. See, that means Q3 means like a 301 plus 1.5 times IQR, which is 65. See? Let's see how much would that be. Okay, 1 point times IQR. Okay, that means 301 plus 1.5 times 65, 398. 398.5 in O, about O, any if all about O, if any data, or if any data for below Q1 minus 1.5 times IQR. Okay, that means Q1 is what? 236 minus 1.5 times IQR is 65. So let's get that one. 236 minus 1.5 times 65, 138.5. 0.5. Okay. They are called outliers or unusual observations. Okay, unusual observations. So therefore, let's go and do some kind of adjustment for this box plot again, and then put that where that uh, the outline. Okay, I'm gonna go this one. Okay, up. Somewhere here, I'm gonna find the upper boundary. It's called the upper boundary to get the outliers. See, that upper boundary is now what we already found. It's going to be 398.5. See, the the below outlier, the lower boundary where the outlier is going to start is how much? That's going to be 138.5. See, since none of the data in this case going to fall, become like outliers, you have that end of whisker, upper whisker or lower whisker. Those are called the whisker. See, whisker. This is a whisker. This is the lower whisker, lower or bottom whisker. See this one, upper whisker. See, can you remember? See, we have a name. See, top whisker. See, bottom whisker and the top whisker. See, upper or top whisker. End of them, see, gonna be minimum and maximum. See, it's cool. Okay. So this one doesn't have a dots. See, no dots. Okay, those are broken lines are not the dots. But there are some situations. Okay, there are some situations you're gonna have the graph like this. See, look at. They stop here. They stop here. But then you're gonna show the whisker still keep going. Okay, this is the whisker. Still keep going, but this time they stop here for a certain reason. That means that your whisker is from here to here, okay? So in this one, your whisker is from here to here. In this case, sorry, your whisker is from here to here. This is the top of the whisker, not this one, not this one, not this one, not this one. This is the bottom of the whisker, not this one. So what happened was, when there are outliers, the outliers will be denoted by the dots. But the whisker gonna go all the way up to this point. That point would be your maximum. This is your maximum. It's the maximum. But it is not considered an outlier. It's pretty much similar fashion. The whisker gonna go all the way down to this point. It's not. That's the minimum. End of the whisker is the minimum. See, end of the whisker is the maximum and minimum. The end of the top whisker is the maximum. End of the bottom whisker is the minimum. See, you can say that this one. See, end of top whisker. Whether you have outliers or not, okay, whisker is what max. End of bottom whisker, the minimum. See, that's the minimum. See, that's the minimum. You have to remember that. Then what is this one in this case? In this case, see, then what is this one? Oh, sorry. Then what is this one? This is the what? The whisk has go and stop at this length is nothing but 1.5 IQR. That's the end of the 1.5 time IQR. This is the end of 1.5 IQR. See? Here. If you don't see that one, your 1.5 IQR is somewhere here. Okay, don't get, it is only when that you have a dots and line. Dots and line, the end of the line is 1.5 IQR. If there's no dots, the end of the line is nothing but, see, but end of the whisker is here. Okay. See, to make it clear, I'm going to write something very, very clearly. Okay, to make it clear, crystal clear. Okay. Okay, this one I'm gonna just do the some kind of a modification. Okay, I'm gonna say end of the whisker, end of top whisker is maximum when there are no outliers. Okay, no outliers. I'm gonna discuss them when there are outliers. Okay, end of whisker is not max. It's gonna be what? End of whisker is for the top one. End of top whisker is Q3 plus 1.5 times IQR. End of bottom whisker is Q3 Q1 minus 1 point times IQR. That's what I want to see. Q1 is Q1. See, that's what I want to emphasize over here. Make it very clear. If there are outliers on the both side or just one side, doesn't matter. Depends on that one. If there are outliers, the end of the whisker, but the way that this one, we don't even consider this one whisker, but if you want to consider this the end of the whisker, see, there are outliers. You see the outliers. This is going to be not the max. This is going to be the Q3 plus 1.5 times IQ. This is the max. Max is over there. But max is not an outlier. See, max or mean are not outliers. See, when you have outliers, you do like that, but this is not considered an outlier. Outlier is anything beyond this point is outliers, but not this guy. This one, since these are dots are outliers. If there are outliers, as I said here, this end of whisker is nothing but Q3 plus top whisker is Q3 plus 1.5 IQR. It's not the maximum. So does with this one. This is not the end of, since these are dots. This the end of this one is not the minimum. The minimum is this one. On the other hand, minimum is not also an outlier, even though it is beyond this point. Okay, it is a dot. It is the where they're gonna start in an ending point. Start in an ending point. See, but this is the end of the whisker. Here they stop over here by 1 point. Q1 minus 1.5 QR. They stop here. See. So look at, I can show you the something here. See. Without whisker. See. No. See, box part of the distribution number that does not show outlier. Very moment it shows the outlier. See, it breaks. Whisk has been broken. See. Whisker stop here. See, where that gonna stop? That's the place that outlier should be. See how the outlier shown as the dot. See, for same distribution that does outlier. See, we stop. Then this one should be the point where this IQR. Okay, like that. If they don't have that one, it's gonna go all the way down. Whisker gonna go all the way down to here. See, end of your whisker would be maximum and minimum when there are no outliers. If there are outliers, this is going to be not the minimum or maximum. This is going to be the Q3 plus 1.5 IQR. This is a Q1 minus 1.5 IQR. This is the minimum, this is the maximum. Okay. Now we have very good clear idea about that, what's going on. Now we can go ahead and talk about this one, and then we have some kind of a issue that when we were talking about this one yesterday. Okay, let's go ahead and look at this picture. The top one, we have a dots, those are outliers, and we have a whisker. Whisker gonna go and stop here, but it's supposed to go all the way up over here, but it's been stopped here because there are outliers, and so does on this side. Okay, so they want to ask about one. As I said, when there are outliers, you are that the your this one. See the last dot. Okay, I'm going to add something to here. When there are sorry, I'm going to add one more thing. I'm going to delete this one. I'm going to say the last top dot is the max, but not an outlier, not an outlier, but not an outlier. On the other hand, the bottom dot is the minimum, but not an outlier. Okay, that's what I want to tell you. See, okay, so the last top one is the max. See? Max for females. Okay, two is definitely. How about this one? This one is nothing but Q3 plus 1.5 IQR. If they have put like an arrow over here to label this one, you can simply say this is nothing but Q3. See, that means if I'm going to show on this side, okay, to make it clear, is there some kind of a before we're gonna you have a this one, you have it like this, then you have a like dots like this. Say you have a dot, dot, dot. Okay, this is nothing but the last top one is the top dot is the max. This point, if you want to know, this is nothing but Q3 plus 1.5 times IQR. This is IQR. IQR is Q3 minus Q1. Okay. This is Q3. This is Q1. This is somewhere you have a Q2. And this is the last bottom one is the minimum. If you want to know this one is nothing but Q1 minus 1.5 times IQR. See, like that. This one, I'm sorry, I'm gonna do this way. This one, and this one. This point, Q3. This point, Q2. This point, Q1. Like, see, if when there are outliers, okay, should be different maximum. See, right. So this one for female max, this for the Q3 for females, this for the Q2 for females, see, median, and Q1 for females, this is the minimum. Okay, so similar fashion, 6 maximum of males, max of males, 6, 7 Q3 of males, 8 median or the Q2 for males, 9 Q1 for males, and minimum for males doesn't matter the end of whisker, not the end of the dot, end of whisker, because this side we don't have a outliers. When there are no outliers, as I mentioned, if there are no outliers, end of, okay, end of bottom whisker is the minimum. We know that. So this is now clear. Okay. Now they're pretty much the same way they're gonna call the Q1. Okay, I'm gonna add something to here. See, what is the relationship between this one? I'm gonna see. I'm gonna get this one. Q1, Q3 sometime we're going to call the third quartile. Or we can, percentile wise, we can say the 75th percentile. See, other name. Then let's say this Q2, this Q2. This is called the second quartile. Or we can say 50th percentile wise. This one is Q1, we can say first quartile. Or we can say 25th percentile. See, that's the idea. And then this is the mean, this is the max. See? If you have outliers, we don't have that. Whisker not going to go all the way out to the max or mean when you have outliers. It's going to stop at Q3 plus 1.5 IQR or Q1 minus 1.5 IQR. We know that. And these are like, they say that you have a distribution, let's say symmetric distribution. See, you have the median at the center, Q2, see, Q2. Then you can divide this one into like equally divide the lower portion. See, that means this one is 25%. This one another 25%. That's why they are percentile wise, we're going to say that 25%. 25% up to this point, up to this point, see, 25% being covered. Up to this point, 50% covered. Up to this point, 75% being covered. See, that's why we're going to call percentile wise 25%. 25%, 50%, and 75%. Okay, like that. See, that's what they were talking about over here. See, the big spot, the big box with the thick line. Thick line is this one we're talking about, this line. The data fall between Q3 and Q1 cut points. Those are cut points, okay? So Q3 and Q1 cut point is Q2. So data that fall between the 75th percentile and the 25th percentile. You know which one is called. This is called the 25th percentile or Q1. This is called the 75th percentile. That's why this 50th. Or the middle 50% of data points. Yes, the data that are in the second and third quartile. See, the data that are in the second and third quartile. See, the big box with the thick line depicts the data that are in the second and third quartile. See, second and third quartile, both of them. See, this depicts both of them. See, this is third quartile. See, it's a third quartile. It's a second quartile. It's a fourth quartile, all the way up to here, fourth quartile. Here, all the way up to down to minimum, first quartile, second and third quartile. See, all the data in first, second, and third quartile gonna be depicted by the 50th percentile. See, that means that in this graph, see, if you talk about this guy, that would talk about data fall in this quartile as well as this quartile. See, up to that point, all the data in first quartile and the second quartile are depicted by Q2 or the middle median. Okay, if we created a box plot and then chain, see, a jitter plot onto it, what proportion of the point would fall inside the box? See, you can remember that when we drew like a jitter plot for the box plot, 50% of data gonna go inside the box plot for sure. Okay, we discussed that. That means that if you have a, say, box plot and the jitter plot together, at least half of the data gonna go inside. See, half of data gonna go inside. See, in this one look like, see, half of them gonna go inside. So does it. This one. So it's it. See, the big box with the thick line would contain the half of the data points, the half that closest to the middle of the distribution. The big box with the thick line would contain half of the data points. Then chain a jitter plot. What proportion of the point would fall inside the box? That's the one thing. The big box with the thick line would contain half of the data points, the half that are closest to the middle of the distribution. this thick line. See? See? Up to that point, they're going to contain 50%. See? So they say, if you created a box plot and the chain jitter plot on it, what proportion of the points would fall inside the box? That's the other thing. If the big box with the thick line would contain half of the data point, that means like they were talking about here, again, if you, the big box with the thick line depicts, this depicts nothing but data gonna all the way up to that point, 50% of data being up to that point. That's why they say, see, up to that point, up to this point, 50% of data being below this one, below this line, including that line as well. Another 50% above that line. See, 50% of data will be below this line and 50% of data above the median. On the other hand, since we have a jitter and both, inside the box also contain 50% of the total data as well. Okay, the rest gonna go to the outside the box. They were distributed in a certain way that you're gonna get the bell shape or right skewed, left skewed distribution. See, inside you're gonna have a 50%, and then you're gonna change that one. See, the color, size, and the alpha stand for that. They're going to give that code for that alpha to get the opacity or the transparency. See, by giving different values, you can play with that one. We did this one last time. We didn't have any major issue. See, then we did this one for that another variable for the box plot and the jitter plot together. See, we can remember it's been chained by the jitter and did some kind of a, just rather than put just the normally that we're going to put, can you remember the way that we put over here when we're going to talk about the jitter plot, box plot and jitter plot together in this coding, okay? I simply say that, see, jitter only, see, there's nothing. But if you want to do some kind of adjustment for the jitter plot, you can say that the height means that how they've been jittered, see, how vertically spread out. See, you can give, and the color for those dots for jitter plots, the gray color, and the transparency, size, how large that would be. If you want to spread out this way as well, that horizontally, then you can talk about even with the width. Okay, we know that all these kind of adjustment. See, what is the IQR? IQR is nothing but the distance between Q3 and Q1 or the height of the box. We talk about that one. And how do we find the IQR? You're going to get the Q3 minus Q1, Q3 minus Q1. If we do, we get out the boundary for the outliers. Boundary for the outliers, you know how do you get the boundary for the outliers that are too low. Fill in the blank spaces with the appropriate concept. See, if you want something, see, Q1, see, Q1, see, Q1 go here. See, how do we figure out the boundary for outliers? See, the way that Q3, if you put the Q3, since we have a negative, when you find the boundary value, see, negative here too, okay? Here negative. This one is 1.5 for sure, see, 1.5. We are talking about the lower boundary because of this negative, okay? They were talking about this guy, okay? I'm going to show you. We're talking about this guy, see? 1.5, Q1 minus 1.5 times IQR. Q1 minus, not the plus, see? Because if you have a plus, you can go with the Q3 here. Q1 minus 1.5 times IQR. How do you find the IQR? Q3 minus Q1, Q3 minus Q1, okay? Now what they're going to do, that they were trying to find out some kind of a model, see? So we can remember that representative relationship among the variable. Now we are trying to do this part. They are heading towards not the graphical representation, the one that I talk about in the beginning. See, we were going to try to get into here. When you have a two variables, explanatory variable and outcome variable, based on their type, whether quantitative or categorical, based on that one, what kind of a procedures, not the graph, procedures can be built up over here. Mainly they are focusing on when you have a y variable quantitative, okay, and then we're going to talk about the introducing a quantitative variable. They're going to talk about introducing a categorical variable. Categorical variable including that discussion. Then you have a group regression. In the beginning, they might not gonna include nothing, neither quantitative or categorical or explanatory variable at all. They're gonna see how y gonna vary by itself. It's called the null model. Then later on, they're gonna add a categorical variable. Then we're gonna call the group regression. See, the group model. Then later on, they're gonna add this one. See, the regression model, like that. See, in a 3-step, they are trying to build this up. Okay. But anyhow, when you're going to write that why you're going to write, see, outcome, come before explanatory tilde, and then after this one, you put the explanatory variable. See, that's the one that they built up over here. But when you put the thumb length equals, see, y equals x, whatever you have, plus other stuff means like where this coming from, the other stuff due to the variation in thumb length explained by the x plus variation in other stuff. The next section we will discuss the other stuff might be, but for now it is useful to think the total variation of outcome variable as the sum of variation due to explanatory variable plus the variation due to other stuff. See, the variation, if you have any variation, that variation is due to what? The variation of this guy plus the variation of this guy. See, the happiness in the countries. Happiness is the y variable, wealth of the country, plus environmental beauty, plus other stuff. You can add as many variable you want for categorical variable, sorry, explanatory variable. See, 2 explanatory variable. But these are, we don't do here, but if we want, you can add. See, it's like a multiple regression. See, multiple. See, if you have a 2 added for the explanatory variable, but still you have other stuff, error, unexplained variation. These are explained variation. This is the total variation for this guy. The total variation, this variation in the happiness in country is due to the variation of this one. This is explained, plus some hidden variations. Those hidden variations are coming due to what? Experimental error, sampling error, different kind of a situation. So due to some errors in that measuring instrument, like that. Those are the ones that we are trying to explain over here. Okay, that means that they are trying to build up some kind of a model. Okay, we mentioned about that one yesterday actually. Okay, so now they are trying to build up the model. Okay, see, model for relationship between the outcome variable and the explanatory variable. This is x, I'm sorry, this is y, this is x. So you're going to say y equals x plus. Another way you're going to say outcome variable equals explanatory, see, explanatory variable plus other stuff. We're going to call that another stuff. That one we're going to say that variation, total variation, okay, total variation on this side, variation, see, explain variation. You can explain this variation. Explain variation plus other stuff means unexplained. That cannot be explained. Unexplained variation. See, that unexplained variation variation of something like that. Let's say, for instance, that if you're talking about the happiness in countries, or if I go to this one, happiness in countries, and the total variation in the happiness in country is due to the explained variation in the health. Plus, there are some more tough that when you're going to measure this one, those are called unexplained ones. Those are the ones that we're going to learn in this side. See? Explain and unexplained. Again, explain and unexplained one you can do real because of the characteristics of the system and induced by the data collection. See? So this one, you can say this one, see? This one again, see? This is due to two types. One is called the real characteristics of the system. System by which you measure that particular variable. The other one is, excuse me, induced by the data collection. When you induce, those are real, okay? The real one are the characteristics of the real. The other one is, see, real one means characteristics of the system. Induce means by data collection. It came by the data, induced by data collection. See, again, when it comes to the induced by data collection, can be due to several things. See, this came through what? Measurement error. You're going to measure that one, some errors. Measurement error. The other one, sampling error. That sample gonna change the way the values of the variable gonna change from sample to sample, or sometimes you're gonna enter data mistakenly. Some units, or sometimes you enter the data wrongly, you give the wrong information, mistakes. See, that's how you're gonna see the variation. See, those variation we're gonna talk about. Later on, we're gonna give a mathematical explanation for this one. See, that's how it works. We're going to talk about the outcome. Outcome means the total variation. Is explanatory variable. Due to the explanatory variation, explanatory variable is called the explained variation. But it's not only that one that's going to be in this discussion. There are some unexplained variation as well. Due to real and the induced by data collection. This is due to the system, some mistakes. The induced one, now when you're going to collect data, there might be measurements error. When you measure something, you measure wrongly, but still wrongly measured, plus that you enter data mistakenly by wrongly as well. And then on the other hand, sample variation is going to sample to sample, you're not going to have the same values, different value. Due to that one, you're going to have that kind of an unexplained variation. That's why they're over here. Okay, let's look at this one. All the source of variation in data are represented in the diagram above, which have adapted from this. Okay. Match example of the source of variation. Measurement error. They say measurement error means some student use a straight, ridge ruler to measure their thumbs, and some user, pliable measuring tape. Some use a pliable measuring tape. Some use the ridge ruler. Some use the ruler. Some use the measuring tape. So they both would not, because of that variation, going to affect that one called the measurement error. They have the measurements not going to be this consistent. See? Somebody use the ridge rule, somebody use the pliable measuring tape. Sampling error. A sample of students from one class statistics had different thumb lengths than the sample student from a different class. So one sample, if you pick a sample of student and then look for the thumb lengths, those thumb lengths not going to be same as the student of the another sample or different class. See? You say the sample of student from one class of statistics had different thumb lengths than the sample of student from different class. That's called a sampling error. You're going to have a different values from sample to sample. Mistake. Some student wrote down the last 4 digits of social security number When asked for the last digit of social security number, those are mistakes. Or you enter data wrong. Okay. Those three gonna go with this one: measurement error, sampling error, mistakes. Those are called induced by this one. The other one very intrinsic. Intrinsic means within the system. These are extrinsic. These are extrinsic errors. These are intrinsic errors. This is the unexplained. See, explained error, unexplained error. See? This is the explained error. Explained error in another way. You can see the variation means error. It's a total error. Total error is due to the total error in that your variable, whichever the variable here, total error. Total error. When you're gonna carry out a certain experiment, let's say the thumb length. See, thumb length. See, thumb length. That variation in thumb length or the errors in thumb length is due to the fact that coming from that explanatory variable. Explanatory variable you can think about due to height. It's explained because of the height it has changed. But there are other plus errors has occurred due to these two called the unexplained errors, unexplained variation, due to that some mistakes in that measuring instrument, measuring system called the intrinsic. Or due to that, when you're going to collect data, you use a measuring unit, different types of measuring units, measuring instruments. So measurement error, sampling variation. See, it's a real the mistakes. Keep going. See, random. Let's take a little bit detour into the notion random. First, let's make a distinction between what we mean by random in regular life and what we mean by random in statistics. To start, let's look at what humans consider random. Students were asked to think of random numbers between 1 and 20 and enter it into a survey. You can try it yourself. Enter a random number between 1 and 20 here. See? How did you decide which number would count as random? See? The results of 211 students entering in random numbers between 1 and 20 are provided by you for a data frame. You know that you can randomly pick a number. See? In a day-to-day life, in a regular life, you call the random, and then what we see the what you call in random in statistics. Okay. So if you can try it yourself, enter a random number between 1 and 20, any number. Let's say I'm going to put 5 here. Any number. See? How did you decide what number would count as random? See? How did you decide? Because any number in between 150 is going to be random number. See? But the results of a 211 student entering in a random number between 1 and 20. 1 and 20 random numbers by the 211 student. That means we have a 211 random numbers provided for your data frame called the survey. The variable is called the any number 1 to 20 holds a number that they enter. Take a look at the few rows of this data frame and make a histogram of this one. Note you probably want to have a 20 bins for 20 possible values of this pair. See? You need this one. How do you get that? Take a look at the few lines of survey. Make a histogram for any. See? Take a look at, in order to look at that few numbers. See, how do you look at the few numbers? It's already done, okay? The variable name is any I20. How do you look at that one? How do you look at that particular variable? See, you can get for the head of that data frame survey. Could that produce that one? If you got the head that and then put that one, that's gonna show that how the numbers would be 7775. To run again, that's not the thing. Survey, lines of survey. See, there's another one. 777. It's getting changed. Same thing. See. See. Now you're going to draw a histogram, see, because it's already set up, okay? They say that these numbers are already picked for this this one. Any all the numbers that they entered, their data set has already set up, okay? Already set up. 7 7 7 7 5 17. Make a histogram. How do you make a histogram? GF underscore histogram. When you're going to put tilde to go that variable into x-axis, the variable name is any 1 to 1 underscore 20 data coming from survey. See, data coming from survey. See? Okay, you do this one again. See, it looks like this one, but on another one that's it looks like this. It's not the same thing. It's a coincidence that we're gonna get the same thing again and again. See, should change. I don't see that it's gonna change. See, it has been broken. Okay. The problem, we know the problem is that we need the bins. Okay. Bin, maybe it is 20 numbers. Let's go with the 20 to make it, see, somewhat like them, the way that they have. See. If you need the color give you here the color, the way they have the gray. Gray color. Then fill. Here they have the yellow. Gray and yellow, see, something like that. Okay. So if you make histogram random number generated from this 20 sided die, what would be the resulting distribution look like? What shape would you expect? See, 200 random numbers generated from a computer or 20-sided die. You can think about the 20-sided die or from if you're on a computer. The same thing, like we're gonna pick some 211 numbers from given numbers 1 to 20. It looks like this one. Look like a bell shape. Like a symmetry. Looks like a sorry, we don't have a bell shape. We have a getting close to the uniform distribution. See, uniform, very close to uniform, not bell shape. Uniform. Okay. So if you're going to increase that one now, see, now this one, see, 1 to 20 numbers, you're going to do 20 times, and then you select the numbers, this one, and resample, and do the same thing. See, you're getting the same thing. That's the same as that one. See, now the student may have many ideas of randoms, including the unpredictable, unexpected, unlikely, or weird. To students in this survey, some particular numbers sound more random than others. They seem to think, for example, that 17 and 7 sound more random than 12, 10, and 15. The mathematical concept of random is different. Whereas we often think that random means unpredictable random process, the way that statisticians think of them are actually high predictable, governed by the probability distribution. Probability distribution shows us the probability for every possible event and thus allow us to estimate the probability of a particular event. If each of the numbers 1 to 20 had an equal likelihood of being selected, we could model that as a random process. just like we did die rolls. Although it is hard to predict which number would be generated on a single trial, we'd be wrong on average 19 out of 20 times. It is highly predictable that we would have a uniform distribution in the long run. See? But student in this one, look at the issue. If we made a histogram of 211 random numbers generated from a computer to enter that, what would be the resulting distribution look like? See, like a uniform, it's getting close to the uniform. Okay, but if you're going to increase this number, instead of 211, if you go to 1,000, 10,000, millions, definitely it's getting very uniform distribution for sure. The larger the value of the sample size, that the more getting closer and closer to its population histogram. Okay, but here says students have many ideas of randomness, including unpredictable, unexpected, unlikely, or weird. See, they might gonna say it's a weird number, unlikely. To the student, see, in this survey, more particular numbers sound more random than others. Some particular numbers sound more random than others. They seem to think, for example, that the 17 and 7 sound more random than 10 or 15. 17 and 7, more random. See, 17 and 7, 17, 17, and see, the 6 and 7, see, more random. They think the 17 and 7 have more random than other numbers. See, 15 and 5. See, that's what they say. See, 15 and 10 and 15. See, 10 and 15. Then to these two numbers are more random. That's why they occur heavily. But in mathematical concept, randomness is different. Whereas we often think that the random means unpredictable random processes. Unpredictable. See? Random processes. See? Unpredictable. Random processes are actually highly predictable. See? Governed by a probability distribution. Even though that it cannot be unpredictable, here these unpredictable random processes are predictable, highly predictable with some kind of a distribution. Distribution means uniform distribution or bell-shaped distribution, right scale, left scale distribution. Probability distribution shows us the probability for every possible event and thus allow us to estimate the probability of a particular event. See? For every event, in this randomness in this case is different. This randomness in this statistics, so mathematically we're going to say that every number can be highly predictable. See? They thought that earlier in a regular, that in a general setting, like see, the day-to-day life, that they thought, see, as I mentioned over here, see, regular life, they thought different way. They thought that two numbers gonna be random, gonna occur more frequently than the other numbers. But in randomness, here means mathematical concept of random is different. Whereas we often think that the random means unpredictable random processes are actually highly predictable. They can be predictable. Any number can be easily that come up with you can show us with the probability for every possible event. See, probability distribution shows us the probability for every possible event and thus allow us to estimate the probability of a particular event. See, if each of the numbers 1 to 20 had an equal likelihood of being selected, we could model that as a random process. See, just like we did die rolls. Although it is hard to predict which number would be generated on a single trial, it is highly predictable that we would have a uniform distribution in the long run. So what that means, okay, I'll explain this one. Here they say that when you think about that, okay, I'm gonna show you this one here. See? They say when they do this one, okay, the numbers, see, I have a number here. number 1, 2, and then this is 18, 19, let's say 20. This is a this is a frequency. If you do this one, see, we're gonna think, okay, something like this, something like that, something like that. We're gonna think that statistically, with the aid of a distribution, okay, that means that if you do this one in a long run, excuse me, in a long run, again and again and again, okay, again and again and again and again, and by increasing, okay, again and again and again in a long run, okay, see, we would have a uniform distribution. See, if you do this one, if you increase that, see, the number of times you are doing that one in the long run, see, I mean like that, see, how many you're gonna pick. Instead of picking here, you pick like a 211, see, numbers, see, 211 numbers. Here may be 10,000 numbers from 1 to 20, from 1 to 20, see. Then they're gonna become like a uniform distribution, see, some distribution, see, that's what they say. Or see, uniform distribution, because this height should be always 1 over 20. See, each one should have a 1 over 20 chance of being selected. See, that's why it's very similar to that die roll experiment. Instead of 6-sided die roll, here you have like a 20-sided die roll. 20-sided die roll, rolled or thrown how many times? 10,000 times. Then it will come to a uniform distribution. That's why that's called the randomness. That's the randomness. The way that we talk about in a regular life is not same as the randomness in this one. See, that's what they say. So now exploring the randomness, see, let us resample like we did before to explore what the results of a random process can look like. We will start the task we just discussed. 211 students asked to generate random number between 1 and 20. But this time we will simulate the data being generated by a random process in which each number has an equal probability of being selected. Each number has equal probability of being selected. Look at that. You go to this one, you have 1 to 20 numbers, side 20. And side 20, you're going to do 211 times and resample it without replacement. Okay, another option to simulate our random sample to skip the extra step of creating the R object side 20. You don't need it. You can put this one inside this one. See, one shot. You can skip this step. Instead of that one, you can put that one inside this one. Of course, we don't save the results of this resample into a vector. We will have done this for nothing. So modify the code below to save the 211 random sample into any 120. See, create a random sample of 211 numbers between 1 and 20 and give the name. See, resample. See, through the resample, you have picked a sample of 211 from the numbers 1 to 20. See, it's been named as any 1 to 20 now. Okay, so side we don't have to say that one. Now it has been put over here. Resample. Now you're going to generate. Okay, generate from that one. This put any new data frame called the computer. Okay, I'm going to put this into a computer. Now make a histogram. Okay, now you have a name of the data set. Okay, so you go gf underscore histogram until your name of the variable is nothing but any 1 to 20, see, 1 to 20, data equals computer, of the data. And since we have that 20, you can give the beans first 20 to join them. Otherwise, they will be like the income variable. See. So the sample distribution would be almost perfectly rectangular if and only we had a rolled 20-side die. No, that's not right. Even a truly random process like 20-sided fair die would really result a perfectly rectangular distribution. Even a truly random process like 20-sided fair die would rarely result in a perfectly rectangular distribution. Yes, very rare. Perfectly rectangular, we never get it. It's very unlikely that the computer-generated random 200 number would be perfectly rectangular because there are random fluctuations. Yes. Large sample would probably look more rectangular than smaller samples. So sample 10,000 would like more rectangular. Yes, that's why I mentioned if you're going to increase this one to 10,000, okay, 10,000 takes a while. No, it's too large for it to work on that. Right? It takes a while. Just say 1,000. It's got stuck. Yeah, it's going to become like this. Okay, if you increase the C, get in C, more perfect rectangular. Okay, see, that's the same thing. That's the same thing they were telling us to tell us to do. That's the same thing I'm trying to do over here. See, here to 11, but that's okay. Okay, then let's go ahead and do the same thing. See, resample this one instead of that one. You put to the 10,000. The same thing I talk about here, and then computer, and then put the this one easy. See. Copy and paste here. Control V. I don't need this one. Put into the data frame and get to the Instagram. Any 20. Probability I2. Any computer. Why they don't come resample 1 to 10,000. 1 to 10,000. Copy this one. Put over here and run. Okay, instead of this one, 10,000. See, I can get it more flat. See. That's called a population version. See, now the quantitative explanatory variable. See, quantitative explanatory variable. Here, quantitative explanatory. Here, quantitative. See, quantitative thumb and density. See, quantitative explanatory variable. See, height. We did this one. Okay, I'm talking about in this discussion. I'm here now. I'm here now. See, quantitative explanatory variable. For that one, we're supposed to talk about the scatter plot. See, we talk about these in large scale earlier. Okay, so now this time instead of called some kind of a qualitative variable or categorical using over here gender, I'm going to use a thumb length being explained through the height. See? Okay, height. See, height. Do you think, okay, we actually could use the same approach with the height as we did with the sex, but we would first need to record height as a categorical variable. We're going to convert this to a categorical variable, get the height and convert to categorical variable, and then just do the same thing that we did earlier. See, look at, see, we try to do that. And later on that, eventually, instead of that one, you go straight and do this one, see. Now, when it comes to this one, this is how I'm here. I'm here. This has catapult. Not only that one, they say that you can do something like this. Okay, this is what I'm talking about. This convert, okay, convert this into the scatter plot. Okay, the another one before that, I'm going to put the 2 for this one. Convert, see, quantitative data into CAD data, and then do the following graphs. Then you can do the following graphs. See, talking about these graphs. See, 2, 3, 4, 5, 6, 7 graphs. See, how do you convert that one? You know how to convert, you know? You know how to convert. That if you need to that one, that code, see, you can see, you can talk about, see, here, see, fingers. I'm going to give there like some kind of a code, fingers, put it back into that one and say height 3 groups, height 2 groups, let's say 2 groups, means entire, okay, entire, you go inside fingers and you selected height and comma 2, and then convert this into factor. Then again you go to fingers, $, height 2, this time you're going to make it factor, see, factor, open, name of that variable name is now fingers, $, height 2 group, comma, then you give the levels 1 to 2, comma, new labels, C, you can say short and tall, short and tall. See, that's another way of doing that. Then you're gonna do all these. Then you can do these curves. See? You're gonna change the name appropriately, okay? But see, you can do, and the one on the other side too. See, this one, this one, this one, this one, and this one. Oh, I'm sorry, all 7, not this one. You don't need the last one. Like that. See, that's what they were talking about. See, that's what they were talking about. See? So, see, Then do the same thing. See? Then if you want 3 category, you can go to 3 category and do that. See? And the last one is the scatter plot, the one that I mentioned here. See? Without doing any that factoring or the convert into the height, convert into the this categorical data, you just simply draw the scatter plot by using this function. See, I did that one. See, GF point thumb height data from the slide. See. Yeah, the rest would be sometimes some kind of a discussion that, but mainly at this stage, see, I think it's a pretty much problem type 1 error. We can talk about those later on. See. See. See, this one we can talk about. See, quantifying this. That's, I mean, like that's the end of this chapter. That mainly that graphical representation of this. This one I can go through them, but before that, I'm going to get into the chapter 5 because this is going to be very useful for you to finish that homework. Quantitative explanatory variable 2, that we did that in 2 ways. One, that by converting that explanatory variable into a categorical variable, or that keep as it is. Okay, so then you can just do all kind of a homework and then midterm test. If you have any questions, just let me know, and then we can continue this discussion or get into chapter 5 or come back to chapter. We discuss about chapter 4, 1 through 4 again, and then move on. Okay, we're going to do the continuation of this one. We're going to, in chapter 5, we are trying to build up the model. That means I'm trying to get in here. Here we did the graphical representation of this 2 variable discussion. In a 2 variable discussion, we are trying to get this guy and this guy. That's it. That's what we are trying to do in chapter 5 and 6, 5, 6, 7. Okay. Thank you very much. Okay. See you guys on Monday and have a nice weekend. Thank you. Bye-bye.